It's your date with the magnetic dipole. A small current carrying coil is a magnetic dipole. I've already posted a video on the electric dipole. On parallel lines, we are going to now analyze, study all the properties of a magnetic dipole. So here you are. A small current carrying coil is a magnetic dipole. If a coil whose plane is in the YZ plane and the axis of the coil is along x-axis, I'm taking the usual right-handed Cartesian. This is x, this is y, then this is z, circle dot. So plane of the coil is in the YZ plane, and if you view it from here, the current flowing in the coil is anti-clockwise when seen from here. Then this face of the coil facing the eye, this is a north pole, and the back one is a south pole. The coil as if is like a bar magnet, So this is equivalent to a bar magnet with this as the south pole and this as the north pole. By the way, for a magnet, the south pole is taken as a imaginary negative magnetic charge and the north pole is a positive magnetic charge. The SI unit of the magnetic charge is ampere meter. Ampere meter. And that exactly is the unit of the pole strength of a bar magnet. Pole strength of a bar magnet. Now, if I break this coil or understand this coil rather as a short bar magnet, and this bar magnet is a magnetic dipole, then all the properties of the magnetic dipole I can link up with the current carrying coil as well. In fact, current carrying coil is a magnetic dipole. If that is so, then this is the axis. This is the axis of the dipole and this is the equator. Once again, my usual style of teaching physics, symmetrical approach, parallel approach. So whatever is your knowledge that you have acquired on electric dipole, why don't you use it in understanding the behavior of the magnetic dipole? So here you are. The magnetic field at the center of the coil, if it carries current I, you all know that, we have done that in the earlier part of the chapter, that is mu naught I by 2R. And the direction of the field at the center, well, the right hand grip rule, that is along I cap, axis of the coil. The magnetic field at a point P on the axis of the coil, we have proved that making use of the Biot-Savart's law, mu naught I by 2 r square upon x square plus r square to the power 3 by 2. And the direction once again is I cap. Mind you, using the Biot-Savart's law, if I ask you to find the magnetic field at any off axis point, for example Q, for example S, you'll put your hands up. Sorry sir, we can't do it. Yes, you can't do it. But then, here I teach you the parallel technique by what I taught you in my video on the electric dipole, which had electric dipole moment P arrow. Similarly, the magnetic dipole moment has magnetic dipole moment small m arrow. And the direction of the small m arrow is from south pole to north pole along the axis. In fact, the direction of the dipole moment is same as the direction of the axis of the direction of the magnetic field of the coil, that is along the axis perpendicular to the plane of the coil. Well, South pole is a negative magnetic charge, North pole is a positive magnetic charge, and then the small distance between them is the dipole arm. Is the dipole arm? Well, in this case, it will be just the width of the wire in which the current is flowing. And for the electric dipole, the dipole moment is QD. So here also it will be QD, but Q here is the pole strength. So ampere meter into meter, that becomes ampere meter square. Well, that's the SI unit of the magnetic dipole moment. So here you are. If I visualize on this parallel approach the current carrying coil also has a magnetic dipole, then this has a dipole moment M arrow, just like the electric dipole moment P arrow. M arrow is Indian Airlines IA arrow. I is a scalar. The area of the plane is a vector. So IA arrow. So I multiplied by pi r square, r is the radius of the coil, of course, I cap. You notice the direction of M arrow is same as B arrow, same as BO arrow, same. And notice that M arrow is parallel to B arrow. That's what I've been saying. Now from the equation 2, let me show you something very interesting. From the equation 2, suppose our dipole anyway has to be something very small. So R is very small and it is much less than X. R is very small, much less than X. It's a small coil. Then in that case, you can neglect X square in this expression, X square as compared to R square. So you get the expression magnetic field at the point P is mu naught I by 2 R square upon R cube. Of course, direction is I cap. That is mu. Now I just do a small trick because I have to bring the area, and in order to have the magnetic dipole moment. So what I do, multiply and divide by pi. So I get mu naught I by 2 pi r square by x cube. Sorry, this was x cube, not r cube. There is a correction, please. This is x cube. R square is neglected as compared to x square. So below you get x cube. Now look at this expression. Now I multiply and divide by 2 because I have to bring in mu naught by 4 pi, the magnetic field constant. So mu naught by 4 pi, I pi r square is m, x cube is already there. So I get the mu naught by 4 pi 2m by x cube I cap. Mu naught by 4 pi is k dash, where k dash is mu naught by 4 pi, the magnetic field constant. Mu naught is the permeability of free space or air, values almost the same. This expression reminds you of the expression of the electric dipole moment and its electric field on the axis of the electric dipole, 2 kp by x cube. There k is 1 by 4 pi epsilon naught. So similar, 2 k dash m by x cube. Beautiful, beautiful parallel analogous approach. So in general, now once I have done that, then in the electric dipole, I showed to you using the polar coordinates, I can do the same. The magnetic field at Q, any general point whose position vector from O is x, then the magnetic field at P due to the dipole is k dash m by x cube into 3 cos square theta plus 1 to the power half. Same expression that we did for the electric dipole. I am reminding you again and again. And the magnetic potential, that was kp cos theta by r square. So here it is k dash m cos theta by x square. Now I can know for this dipole even the magnetic field at the equator a point S. At the point S on equator, Well, there it was Kp by x cube. Here it is K dash m by x cube.
And want me to make more useful videos for you? Subscribe my channel and hit the bell icon to stay updated.